Today we're going to look at section 8.2. We are going to identify characteristics of similar figures. So let's talk about what similar figures are. Similar figures are figures that have the same shape, but not necessarily the same size. Okay, so in the past, we've always talked about congruent figures, like congruent triangles, where they had to be the same shape and the same size. So similar means that the shape is the same, but their size might not be. So here's just a picture of several different figures that are definitely the same shape, but as you can notice, one is a little bit bigger than the other, so they're not the same size. A dilation is a transformation that produces an image that is the same shape but a different size. Okay, so that's why it goes hand in hand with a similar figure. Dilation is creating two shapes that are same but not necessarily the same size. So it's going to either stretch or shrink. So if we look at this picture right here, notice that we have two triangles on a coordinate plane, okay, because we have an X and a Y axis. Technically, because we do have an X and a Y axis, we do have perpendicular lines because the X axis and the Y axis are always perpendicular. So we do technically have right triangles, okay? So triangle EMD and triangle CMN are right triangles. So that's why not only are they triangles, but they're right triangles. So that's why they are the same shape. But notice that one triangle is inside of the other. EMD is a smaller triangle than CMN. Okay, so notice that I've given us some ordered pairs. So let's kind of talk about what each of those side lengths are. So let's focus on the triangle of CMN first. Okay, so notice that there's three sides. There's the side CM, there's the side MN, and then there's the side CN. So notice that the side CM, well, M is at the point 0, 0, and C is at the point 0, 8. Notice that because that is on the y-axis, I want to focus on the y values of the ordered pairs. Remember, in an ordered pair, X goes first and Y goes second. So I want to look at the second 0 for M, and then the 8 in that ordered pair of 0, 8. So how did I go from M to C? Well, that became a length of 8 because 0 to 8 is a length of 8. So then if I look at the length of MN, notice that that's on the x-axis. So I want to look at the ordered pairs for M and N, but I want to look at the x values. So the first numbers in the ordered pair. Well, at M, it's 0. At N, it's 6. To go from 0 to 6 means that we have a length of 6. So then looking at the segment of CN, it is on a diagonal here. It's slanted. So I can't just count numbers. This is where we have something called the Pythagorean Theorem. Okay, when you have a right triangle, and this is something that we're going to talk a lot more about in another chapter, but maybe this is familiar. When you have a right triangle, we have something called the Pythagorean Theorem that a squared plus b squared is going to equal c squared. So essentially, CM and NM are the A and the B. Okay, those are the legs of that right triangle. C is the hypotenuse, what's across from the right angle. So if I was to substitute 8 and 6 in, we'd have 8 squared plus 6 squared, and that's going to equal c squared. Well, 8 squared is 64, 6 squared is 36. Notice that when I add those numbers, I'm going to get 100. And then to get rid of a square, we take the square root. Now, normally when you take the square root, you have two answers, but because this is representing the length of something, I only want the positive number. So the square root of 100 would be 10. So there are my three different lengths for that triangle. Now, if I look at the triangle of EMD, that's the side of EM, that's the side of MD, and that's the side of ED. So EM, notice that that's on the y-axis. So if I look at the y values, to go from 0 to 4 is a length of 4. Looking at MD, it's on the x-axis. So looking at the x values, to go from 0 to 3 would be a length of 3. And then we can do the same thing. We can take those two, those are the legs. I can plug it into this Pythagorean theorem. So 4 squared plus 3 squared is going to equal c squared. Well, 4 squared is 16, 3 squared is 9. That still equals c squared. Add that up, we get 25, and we have to take the square root. Notice that once again, because I'm finding the length of a side of a triangle, I only want the positive value. That's going to give me 5. So if you look at the relationship between the numbers for the triangle CMN and the triangle EMD, notice that from 8 to 4, it's cut in half. From 6 to 3, it's cut in half. From 10 to 5, it's cut in half. Or you can go the opposite. 4 to 8, you double. 3 to 6, you double. 5 to 10, you double. So if I wanted to compare triangle EMD to triangle CMN, I would say it's in the ratio of 1 to 2. Because once again, EMD is the smaller, and I have to double each of those sides to get to the 8, the 6, and the 10. So that's kind of the relationship there. All right, so now let's talk about similar polygons. So remember, a polygon could be a triangle, a quadrilateral, a pentagon. It can be all of those things that we talked about in Chapter 7 first semester. But there's 2 characteristics to be considered similar. The first characteristic deals with the sides. The ratios of corresponding sides are equal. The second characteristic deals with angles. Corresponding angles are congruent. So if I look at this picture, we've got 2 triangles. We've got triangle ABC and triangle DEF. So from this, we are going to prove that triangle ABC is similar to triangle DEF. So notice that the similar triangle, or the similar symbol, is a little tilde. Okay, so this symbol represents similar. Obviously, this symbol represents equal. And then this symbol represents congruent. So notice that congruent is both similar and equal. So take the pieces of a congruent symbol apart and you have similar and equal. Okay, so we're going to prove that those 2 triangles are similar. Looking at the characteristics, it has to deal with the sides and the angles. So the first thing deals with the sides. Corresponding sides are equal. Ratios of corresponding sides, excuse me. So that means that if I'm looking at the 2 triangles that I want to prove similar, the order of the letters matter, just like it did when we were talking about congruent. So notice that I named it triangle ABC. So the first 2 letters are AB. Notice that in the second triangle, the first 2 letters are ED. And I set it up like a ratio. So those 2 sides are corresponding. I need the ratio to then equal the ratio of the next 2 letters that I get together. And then the same thing with the third side. I need 3 ratios because we have a triangle here. So notice that AB is a length of 8. Notice that DE is a length of 4. So notice how this then simplifies down to 2 over 1. So that means I'm hoping that my other 2 sets of ratios that are corresponding sides also are going to reduce down to 2 over 1. So let's pick 2 more letters. Let's pick AC. So notice that's the first and the last letter. Moving on to the next triangle, that would be DF. So let's figure out this ratio. AC would be 12. DF would be 6. Notice that when I simplify it down, it gets me 2 over 1. The last side in the triangle would be BC over EF. Notice that BC is a length of 10, EF is a length of 5, and notice that that also reduces down to 2 over 1. So every single one of my ratios of corresponding sides reduce down to the same thing. So that proves the first one, that ratios of corresponding sides are equal. So now we have to have corresponding angles congruent. Well, notice that angle A is first. Notice that angle D is first. And notice that they're marked the same. They both have those two little squiggles inside of the vertex. So those are congruent. Notice that angle B has the same markings as angle E. Those are corresponding angles because those lie in the same spot of my triangle. And then same thing with angle C and angle F. So we just proved, because of those two pieces of ratios of corresponding sides to be equal and corresponding angles to be congruent, that we have similar triangles. All right, so let's take a look at this example. So notice that now this is the opposite. I am giving us that we have similar figures. This time we have quadrilaterals because we've got 4 sides. So I'm giving you similarity, which means that we already know that ratios of corresponding sides are equal and angles that are corresponding are congruent. In part A, they're asking for us to find the side FG, GH, and EH. So because we're dealing with sides, then we just need to focus on that first piece of information, that ratios of corresponding sides are equal. So if I look at the order of the letters for these similar figures, I'm going to just set up all the different ratios of corresponding sides. So because we've got 4 sides, we should have 4 ratios of corresponding sides. So AB is first, and I'm going to put that over EF because those 2 letters are first. Okay, because I started with AB, so I'm going to put this as the numerator. And then I'm going to put this as the denominator. I can never switch that, okay? I have to stay consistent. Whatever I put on top first, then that means that all of those pieces from that particular figure is going to have to go in the same spot when we are naming our ratios. So then I'm going to say the side BC. So notice that that would be then over FG. We've got the side CD. So if you look at the order of the letters, that would have to go with GH. And then if we look at the side DA, that would have to go with HE. Okay, so there is the ratio of all of my corresponding sides that are equal. Now what we want to do is we want to start plugging in the numbers for what we know. Well, I know that AB is 6. I know that EF is 9. I know that BC is 4, and notice that I do not know what FG is. So I can ignore the other 2 ratios for a second because here we have a proportion just like we did in the first section, and we can solve a proportion by cross multiplying. If you like, you could simplify down the 6 over 9. 6 over 9 would simplify down to 2/3. And then if you're doing it in your head, it will be easier because we'll have smaller numbers. So then when I cross multiply, we'll have 2 times FG to equal 3 times 4, which is 12. So then I'll divide both sides by 2, and it looks like we get a length of FG to be 6. So there's one of my answers. Now, because that very first ratio has the same or has 2 numbers, we're going to keep that ratio, and then I can set that equal to the third ratio of CD over GH. And then I can take the first ratio that has 2 numbers and set it equal to the last one, because in each one of those, there should be one unknown. So I'm going to keep it as the 2/3. I'm always going to keep it as that reduced thing for me. But now I'm going to put it over CD and GH. So CD is 3, and then GH is what we're trying to find. So then if I cross multiply, we'll have 2 times GH equal 3 times 3, which is 9. I'm going to divide both sides by 2. So if you want, I'm going to leave it as just a fraction reduced down to lowest terms. 9/2 can't be simplified down any further. So I'm just going to keep it as 9/2. If you made it a decimal, that's okay. Just because this would not be a repeating decimal, it would just turn to 4.5. But if there was some kind of really long decimal, just leave it as a fraction. Okay, so then the last one we have to find is EH. So once again, I'm going to go back to that very first ratio that gave me 2 numbers, 6 over 9 reduced down to 2/3. And now I'm looking at the very last ratio. DA is 7 over the unknown that we are trying to find. So then once again, I'm going to cross multiply. We're going to have 2 times HE to equal 3 times 7, which is 21. I'm going to divide both sides by 2, and I'm going to leave it as a fraction again. You could reduce it down to a decimal just because it would be 10.5. But if it was like I said, some kind of like repeating decimal or some really long decimal that didn't have an ending to it, just leave it as a reduced fraction. Okay, so those were my answers for those 3 segments. So if we use the same figures, I know that they're similar. It says find the ratio of the perimeter of ABCD to the perimeter of EFGH. Okay, so essentially perimeter we know is where we're going to add up all the sides. ABCD, well, we know that one side is 6, one side is 4, one side is 3, one side is 7. So when I add that up, 6 and 4 is 10, 3 and 7 is 10, 10 and 10 is 20. If I add up the sides that we just got for part A, we can find EFGH's perimeter. So we have 9, we had 6. If I wrote it as a decimal now, 4.5 and 10.5. So when I add up all of those, we would get then 30. So if it says find the ratio of the perimeter of ABCD over EFGH, that means I would want to put the 20 on the top and the 30 on the bottom. Notice how we always want to reduce ratios down to lowest terms, and that would give us 2/3. But notice that 2/3 is actually a number that we've seen before. If I go back to part A, notice that 2/3 was that number that ended up reducing down our one ratio of corresponding sides. That is not a coincidence. Essentially, the ratio of the perimeter of 2 similar polygons will equal the ratio of any pair of corresponding sides. Okay, so that means that we could actually, instead of, if I didn't have a problem where it asked me to find all 3 sides of a missing figure, as long as I know the ratio of corresponding sides between the 2 figures, and I know the perimeter of one of them, I can find then the perimeter of the other, and we can go that way. All right, let's take a look at another example. I'm given us similar triangles, JHK and POM. I'm giving us angle H to be 90, angle J to be 40, angle M to be X plus 5, and angle O to be 1/2 Y. So notice this time, because everything that's given to us in terms of our similar triangles is dealing with angles, we're going to use that second relationship that corresponding angles are congruent. So let's name which corresponding angles are congruent. Notice how angle J is first in the first triangle, angle P is first in the second. So that means those are corresponding, they're congruent. So that means that angle H would be congruent to angle O because they're both in the middle. And angle K is going to be congruent to angle M because they're both the last. Okay, so notice that I know that I've got right angles for H and O, so I knew that they had to be congruent. Because angle J is 40, we could find the measure of angle K very easily because remember, 3 angles of a triangle add up to 180. So to find angle K, I can do 180 minus 90 minus 40. So we would find out that that is a 50-degree angle. So that's going to help me when I want to find X, because notice that angle K is congruent to angle M. Angle M is X plus 5. Congruent means equals, so I'm going to set that equal to the now measure that I know, which is angle K to be 50. So all I have to do to find X is subtract 5 from both sides, and so I know that X is 45. To find Y, that means we have to use angle O, which is going to be congruent to angle H. Well, angle H is 90. Angle O is this 1/2 Y. So how am I going to get Y by itself? There's 2 different ways you can think of this. You can divide by a half, or you can multiply both sides by that reciprocal. The reciprocal of 1/2 is 2. So 2 times a half is going to cancel that out, leaving you y by itself. But if you do it to one side, you got to do it to the other. So that means that 2 times 90, which is 180, gets me the value for y.